Hi class, this is your instructor again. I'm Todd Yurchisin for PSC 2121, Fundamentals of Physical Science. And again, you recall that I'm teaching some basic things of physical science that use principles some really basic principles in science to teach things like astronomy and geology and such. And we're picking up again today with the remainder of plate tectonics. As you recall, plate tectonics is the movement of the outer lithospheric plates on the asthenosphere of the Earth, and they move around because of internal heating from below, the convection currents. We're going to talk about today the different kinds of plates that there are and when they interact with the other ones and what happens there, because different things happen in different places. Yes, this is testable material, so take good notes. And then we're going to go through, and then there's a couple of other places on the Earth that things are happening, but it's not at a plate boundary. There are a couple of exceptions called a hotspot. So let's start with the types of plates and boundaries. There's three kinds of boundaries, and you can imagine just the three different combinations of how they can interact. You could have a divergent boundary. That's where where something is happening and they're pulling apart. Plates themselves are pulling away from each other. Another one you could have is where they're coming towards each other. And another one they're sliding back and forth. So we call divergent boundaries where the new crust is generating as the plates pull away from each other. And this happens for instance, it happens here is some hot material coming up. It's pushing on this oceanic crust. Remember, it's relatively thin, and it's going to push it apart. Material is going to come up. As it gets to the water, it's going to cool. So it's going to add to the crust, and it pushes these things apart. So if it's pushing it apart, it's going to add to it. More stuff comes in. It cools, adds to it. So you can see these plates moving apart like this as a divergent boundary. Convergent boundaries are where crust is destroyed as one plate dives underneath the other. As these things come together, one of them is going to go underneath the other one. I'll talk about that. So they're converging. Converging means to come together. Over here you have two oceanic plates coming together, and some stuff is happening here. And then a transform boundary is where the crust is neither produced nor destroyed as they slide horizontally back and forth next to each other. The most famous example of that would be the San Andreas Fault. So let's talk about divergent boundaries. So divergent boundaries are where the plates are moving apart from each other, and new crust is created here. So that's one of the characteristics. New crust is created. Magma comes up. As it comes through here, it's generally underwater. Most of the divergent boundaries you're going to find on the Earth are underwater. There are a few that are on land, and I'll tell you about that in a second. As it gets to the water is, of course, much cooler. It's going to cool off that rock, take the heat away, and it's going to add to the crust, and it pushes. You can see that here's the lithosphere riding on the asthenosphere. You can see that as it adds to that, it pushes this away. And in the Atlantic Ocean, it happens about, I think, an inch per year or something like that. Molten material from the mantle rises to fill these fissures. It says often accompanied by volcanic activity. Underwater, yeah, sometimes it comes out fairly violently. So they've literally have photographs of movies of some underwater volcanoes, but much more so on land. And we'll talk about the ones that are on land in a few moments. The best known is the Mid-Atlantic Ridge. All down the middle of the Atlantic Ocean, there's this very large crack, and you can see that's where South America was attached to Africa, and there was a rift here, a divergent boundary. There was something hot coming up and pushing it up and broke it apart, and so all of this ocean on this side and all the ocean on this side have been forming since they've been spreading apart. So where's the oldest part of the ocean? Where's the oldest part of the Atlantic Ocean? It would be along the coasts of South America and North and Africa, wouldn't it? Most of that rock there is much older, and as we come closer to the rift, that's much younger rock because that's the stuff that's come up more recently and has been pushed apart. The rate of spread is about 2.5 centimeters per year, about an inch per year, or 25 kilometers in a million years. So 1 million years geologically is not real. I mean, it's not slow, but it's not real fast. So 25 kilometers in 1 million years, you multiply that by 50 million years, then you've got a pretty good sized ocean going. The seafloor spreading over the past 100 to 200 million years has caused the Atlantic Ocean to grow from a tiny inlet to this giant ocean between the continents. You can see the material coming up. As it comes up here, this heat here weakens the lithospheric material. It breaks through, and remember, this material is coming up and spreading this way. So friction is also wanting to pull these continents apart, these plates apart. Remember, the material is coming up and going and circulating back this way. So it's pulling the crust apart like this. Material comes up, cools, adds to the crust, and that process continues. So if that happens like that, then something must be happening at the other end. It has to go somewhere. Mid-Atlantic Ridge, again, here's another map of this, and got some color coding here. The yellow is the oldest stuff, and as you go along, and they've got it color coded as to the age of the rocks. In other words, where the rift is itself, 0 to 5 million years old. How do we know this? Well, we talked about advances in science that allow us to have submarines and such that could go that deep and sample and take rock samples and cores. Remember, when this first came out, when the idea that these continents were together, we didn't have that kind of machinery, and so the geologists said, oh, that's just a bunch of bunk. How could they move? It doesn't make any sense. But like most progress in theories, in scientific theories, it usually comes about as progress in our technology also. We improve our instruments, we improve our vehicles and such so that we can actually determine these things, because now we have the equipment that can test this and detect this kind of thing. So as the material comes up, it circulates, the material comes up here, forms a rift valley, the molten material underneath spreads this way, it's going to be dragging above it, the crust with it, and then it drops back down again at the trench. I'll get to that in a little bit. And let's see, some drilling evidence. We've drilled. Older fossils and rocks are near the continents. In other words, over here, this is where we find much older fossils. Remember, there's animals that live in the ocean. There's animals in the ocean, and they die off and they sink to the bottom. And as they do so, they're going to form a layer on the bottom here. And as you can imagine, the older animals are going to be under here, and of course going to be covered with much more sediment, going to be deeper in underneath the crust, further down in the crust. And much younger animals, much more recent animals, are going to be spread towards the center. So we have fossil evidence to show this too. This is a picture. I just had to throw this picture in. I just thought this was really neat. This is a photograph of the Mid-Atlantic Ridge as it crosses through Iceland. Iceland is a hunk of land that's sitting right on top of the Mid-Atlantic Ridge. And it's formed pretty much, remember, there's volcanic material coming up. And in most places it stays underwater. But for some reason in Iceland it's maybe a little warmer there, a little hotter, deeper underneath the ground or something. So enough material has come up to form this rather large island, which we call Iceland. And this is a picture of the Mid-Atlantic Ridge, literally. This is spreading apart, and they've got a bridge over here. It's Leif the Lucky Bridge straddling the Mid-Atlantic Ridge. And I imagine perhaps on one end or the other there's rollers there. It would have to have rollers there because as it moves an inch per year, roughly, then this bridge, maybe every so often they have to go out and put a few more boards in the bridge and make it a little bit longer. Picture of the Mid-Atlantic Ridge without the water, no water here on the Atlantic Ocean, and you can see this rather large rift all the way through the ocean, all the way across. You see these lines that are perpendicular to that. I'll talk more on this later, but those are transform boundaries. That's where the plates are sliding like this. So on this side relative to this side, they're sliding a little bit back and forth. So you can see that it's not just a straight line. Look how much this one has moved this way and that one's moved that way along this transform boundary. I'll give a little more detail on that a little bit later. So let's look at some plate rifting and divergent on land, on a continent. We talked about it in the ocean. Let's look at it on land. We have rising currents in the astronosphere. Here's a hot spot. Here's some very warm material rising. It stresses this area here. It's going to heat this up and warm this, and as it's coming up, it's pushing on this, and it's causing a stress area here, and it wants to push this apart. As it does so, as it starts pushing this apart, it starts to melt the material above it, and the rock caves in, collapses in, and the material collapses in, and it's going to form a low point. Well, what happens to most low points on the land? Water fills in there, right? Water's going to find its level, and it's going to fill it in. So most of the time, when we see a continental rift right in the middle of a continent like this, then it's usually a river or lake or something going on there. And here it is further, as it pushes these continental plates further apart. All this area here colored green is the new material, new oceanic crust material. It's coming up, and I already talked about how the oceanic crust forms. That's what's happening here. And the water is filling in, and these landforms here are getting further apart. This is what's happening in East Africa. For those that have heard of Mount Kilimanjaro, Lake Victoria, Lake Tanganyika, and the rift valleys in Africa, you've probably heard of these. This all along here is a rift area. These are spreading apart here. They're coming apart. And so all of this here is probably going to break off. You can see, you practically see it in this photo here, or this depiction here, that this is eventually going to break off here as material comes up and breaks this off. So you can see where this is eventually going to break off. The lakes here are filling with water because they're lowlands here. And Mount Kilimanjaro, is this very large, semi-dormant volcano in East Africa, and it's probably as a result of some volcanic material here. The Afar lowlands, there's villages here, and every once in a while you hear about earthquakes and some lava flows and such in this area. There are some villages here that are affected by that, and it's because of lava flowing out from this rift area here. So for a divergent boundary, some characteristics of this, it's rifting, it's breaking apart. Are you going to have volcanic volcanoes? Well, not volcanoes in the sense that you would think that they're erupting like Mount St. Helens or such, but you're going to have, what I mean here is lava flow. You're going to have some flow. Some material is going to flow. And it's also characterized by, you could have earthquakes. So that's divergent boundary. And here's a summary slide of all of this. Again, materials coming up, breaking apart this lighter continental crust material, starts pushing apart these plates. Continued stress, this material flows in here, melts, and new materials coming up, and this is flowing apart, and eventually you could end up with an ocean or at least a seabed, and this one continent, single continent, has now got separated by quite a bit of water here. All right, convergent boundaries. These are when two plates move toward each other, and there's three kinds, based on the three combinations of how they could come together. There's two kinds of plates. There's the oceanic crust, and you have the continental crust. So you could have an ocean and a continental crust coming together. You could have two oceanic crusts coming together, and you could have two continental crusts. I mean, obviously those are the three combinations that you have if you have two different types of crusts. So let's talk about, let me put up here convergent. And you have, let's talk about the ocean to continent. That's the one that we seem to be most concerned with because we're on the continent and things are happening at each end here. The old crust is destroyed in the process. What happens is one of lithospheric plates is going to dive underneath the other one. As it does so, this material down here, what's going to happen to it when it gets into the asthenosphere and goes deeper and deeper? What's going to happen to it? It's going to melt. It's going to be destroyed, and it's going to be recycled. So, and we call that the subduction zone, where these things go, where one goes underneath the other one. It's a subduction zone. Notice that in the continent to continent, we don't have much of a subduction zone. All right, so the ocean to continent plate. Oceanic plate is denser. Remember, I said that before, that it's made of basaltic material. It's much denser in composition because of the way it was formed. The way it was formed, it came up and was solidified and cooled fairly quickly when it got to the water of the oceans. And so it's much denser. And so when it gets to the much less dense continental crust, what's going to happen? It's going to go underneath it. It's going to dive underneath it. And when it does so, here is the continental crust, here's the ocean crust. As it does so, it's going to be pulling on it. Remember, over here is a circulation. It's circulating like this. So it's pulling it and it's being pushed over here by the divergent boundary. As it goes, it dives under here, and it's putting pressure on this area here. There's pressure here. It's pulling on it. It's kind of pulling on it down as this moves this way. As it pulls on it downward, eventually it can't keep pulling on it. It's going to spring back. And as it springs back, that's an earthquake. That's what an earthquake is. And also, it's going to push on the water, and it could have a pretty bad tsunami there too. Anyway, the crust itself, as it goes down, further down, it's going to start melting. But it's made of, while it's made of denser material than the continent, this material is also less dense because it's got a lot of material from fossil material and such, so it's not as dense. It's going to melt, and it's going to come up, and it will come up through, and it's heated, and it comes up onto the continent and form volcanoes. And when this happens again and again and again, you build up a mountain range. And so we see on our maps, I'm going to show you, we see a lot of high peaks and volcanoes, like in northwestern America with Mount St. Helens and Mount Rainier. That mountain range there, the Cascade Mountains, are formed in this fashion. Because the continental crust is being pulled down like this, as we do, it forms a trench. And a trench is merely, it's just very deep there. It's very deep because it's pulling on it. So characteristic here is we have a trench, and we have earthquakes, and we're going to have volcanoes. Volcanoes come from the fact that this material is coming down, melting, coming back up again. The trench is because as these things interact, as this moves down here, it's pulling on this downward. Here's a picture of South America. Now remember, South America is moving in which direction? If it's pulling away from Africa, then it's moving in this direction. And over here is the Pacific plate. The colors on this map represent altitude. The highest altitudes are the red and the brown. The lowest altitudes are the blues. So here, the lowest altitude here is this very dark blue all along here, and you can see this very deep trench as the continental crust is moving over top of it's being pulled down like this, and it's forming this very deep trench all along here. And as you get further away from the trench, it gets more shallow again. So you can see this all along South America. And then what do we have along here? Mountain ranges, as some of this material is pushed up, and also some volcanic material has been released and pushed up and made into these mountains. How many times do you hear about an earthquake in Ecuador or in Argentina or in Chile or something? That's because it's all along here. This is where the action is. This is where things are happening. So what's driving this? Again, you have the rising convection current as it comes up and moves this way. Over here in the ocean is the divergent boundary. Material's coming up. It's adding to the crust. It's cooling quickly. It forms the oceanic crust. It's denser than the continental crust, and so it's going to ride underneath the continent as these things converge. As this goes down underneath, this is being pulled a little bit. It's going to form a trench. We call this, where these interact, the subduction zone. So there's another vocabulary word for you. Subduction zone. And that's only for the ocean to continent and ocean to ocean plates. We don't get one with the continent to continent. I'll talk about that in a few moments. And like boiling water that's hot in the center, this convection current is driving this. As this material goes further and further down and deeper, it's going to start to melt because it's getting hotter and hotter. In this material, well, and as it goes in, it's going to come up and it's going to form mountain ranges. And you have, here's a crater lake. There's a lake inside of an old dormant volcano. And so you have characteristic, you have these mountains like this along the northwestern America and South America. As this material comes down, what's in this? What is in the oceanic plates? Well, lots of fossils, lots of sea animals have floated down and joined the soil and such, and lots of water is in it. Because remember, there's lots of pressure of water pushing into this material. So this has got lots of water in it. Well, water, when you put water in, mixed in with some of these minerals and such, the introduction of water from the dehydrating oceanic crust drops the melting point of the mantle. In other words, because there's water there, it makes the melting point of this material lower. So water is forced out. Well, water is much less dense than the other stuff around it. And it's also hot and it's steam, so it expands and it wants to come back up again. So the rising current of warm mantle wants to come back up, and it's got water in it, and it's going to come up and it's going to make a nice big volcano. If you look at some of the volcanic material, yes, there's rock and granite and all kinds of stuff in it, but there's also lots of water, also lots of CO2. Where does the CO2 come from? From a lot of these, from a lot of the life material that has died and has settled down onto the crust. And it's actually part of the carbon dioxide cycle. So it's a way for us to keep carbon dioxide out of the atmosphere, is by this dead material going down and getting absorbed into the earth. All right, so an ocean-to-ocean plate convergence is pretty much the same, pretty much what I just discussed. A denser plate is forced under one or the other, but wait, Mr. Todd, they're both the same. They're both oceanic crust. How could one ride underneath the other one? Well, because they're both dense, one's going to come underneath the other one at some point. It's going to be forced underneath. How that exactly happens, couldn't say, not a geologist, but one does. For our purposes, it happens. And otherwise, the characteristics are very similar. Here you have the oceanic plate, here you have the other oceanic plate, it's coming down, and as it does so, it pulls on this, and it forms a trench. You have a trench forming there. So we have the ocean to ocean boundary. This is the boundary. And you have the same thing. You have a trench forming, you have earthquakes, and you're going to have volcanoes. It's pretty much the same as the other one. As a result of this, you have some earthquakes along here, and you're going to have volcanoes. And so you may very well have island arcs formed along here. As the ocean plates meet, you have volcanoes along there, so you have lots of volcanic islands. If you look at a map where these ocean plates meet, Japan is a great example. Japan is a result of volcanic activity. How many times a year you hear about some volcano or something going off in Japan perhaps, or an earthquake or something? Hawaii is not one of these. I'll get to Hawaii later. Hawaii is not one of these. Here we have the North American plate, and it's moving roughly this way. The Juan de Fuca plate is moving down and it's overcoming, and you have some subduction here, and you have material coming up, and you have the Mount St. Helens volcano here and Mount Rainier and such. And over here, as it goes around this way, the Aleutian Islands, all these islands here have all been formed volcanically from from the ocean to ocean plate. These, and what is a volcanic island? What is it? It's merely when there's volcanic material coming up and settling on the ocean floor, and it does it again and again. It just happens to break the surface. Happens to break the surface of the water, and you've got an island there. So that's what's the Aleutian Islands here. That's pretty much how they were formed. Okay, and then finally the continent-to-continent plate convergence. You don't see this very much on the planet. We don't have very many of these, but the best example is India crashing into southern Eurasia. And the less dense granite-type materials resist subduction. Because they're lighter weight, they don't really subduct underneath. One doesn't go underneath the other one. So what happens is the colliding plates pile up. Instead of subducting down, they pile up, and they push mountains up. And an example of that is the Himalayan and the Rocky Mountains. The Rocky Mountains in the center of, pretty much the center of the United States. Those are being pushed up, the plate moving slightly that way. And as these crash together, there's a little bit of push here, ancient oceanic crust here, and it will melt. Here you have two continents coming together. Here's the oceanic plate converging with the continental plate, and you have all the stuff that I was telling you before with volcanoes going such. And as the continents merge, then they're going to push on each other, and you end up on either side of this, what was lowland, you end up with highlands forming, coming back up again. This is India. So here's the Indian plate, very old rock, 2 to 2.5 billion years old. Here's the Eurasian plate, and as it comes together, part of it's sliding. It's pushing up the Eurasian plate. The rising Tibetan plateau is getting higher and higher, and the Himalayas are going higher. So in other words, Mount Everest, the highest mountain in the world, is actually getting even higher. When two continents collide, then neither is subducted. And then the slow, continuous convergence of these two plates over millions of years makes the Himalayas and the Tibetan plateau rise. Most of this has happened during the last 10 million years. Okay, and then finally, transform boundaries. And before I jump into that, let me do a quick review of all that. Let me do a quick review of convergent boundaries. So for ocean and ocean to continental plates, you're going to have earthquakes, you're going to have volcanoes, and trench. But on continent to continent, why am I writing it out on the board like this, by the way? Because, hey, it makes a great test question. You know that if I'm writing it out, there must be a reason. It's a great test question. So for continent to continent, you could have some earthquakes. There are earthquakes there, but no volcanoes and no trench, right? We're not going to have volcanoes. There's no volcanic material there. There's nothing coming up. And no trenches because we're not pulling down anything. Everything is being pushed up. So that's all we're going to have there. All right, transform boundaries. This is where the boundaries are sliding back and forth past each other. The crust is neither created nor destroyed. Nothing's created or destroyed there. They're just merely passing back and forth across each other. But what we do have is earthquakes. Why? Because you have, what I'm doing here is I'm going to move, one of my hand is moving this down that way and the other one's moving this way. If you push your hands together like this and then try to move them, nothing happens. They don't really move, and then all of a sudden there's a slip. Try this on your own. Just push them together and then move them this way relative to each other. And you'll notice that nothing really happens and then there's a slip, and then nothing really happens and then there's another slip. and you can feel it, and there's just this rather large break. It doesn't happen gradually. You're not doing this. It builds up pressure, and then it slips a little bit. And that's an earthquake. That's what happens with these plates on the Earth. And since they're just sliding past each other, it doesn't have the features of convergent divergent boundaries. Sudden jerks produce earthquakes. Most of them are found on the ocean floor. You see a lot of that zigzag pattern that I showed you earlier going across these ridges. Some occur on land. Most famous one is probably the San Andreas Fault. May be seen as linear valleys where rock has been ground up by the sliding. And may be seen as you see stream beds. You'll see a stream bed, and it's now part of it's over here, and then the water has to find a way to do this. Here's transform boundaries. Here's again, the astronosphere, the hot pieces coming up, pushing this part. What's this called again? What's this one called? Divergent boundary. Pushing this material apart and adding to it. As it moves this way, remember, it's being pulled this way and forced with an added material here, pushing this along this way. It reaches the other side, and over here you have a convergent boundary. The plate is subducted down underneath, heats up, broken up, comes up as volcanoes. But along here, along this rift here, some places are moving a little bit faster than others. So this is moving, they're both moving apart, but all along here you see that, the actual rift itself has been broken by transform boundaries, and again, they're just sliding next to each other. So you can see this by, in some photographs, you can see a river stream bed has been offset by a transform where they've just moved laterally next to each other. Here's the San Andreas Fault, Los Angeles down here, San Francisco here. Someday, Los Angeles will be up here next to San Francisco. You won't have to fly, you can just get on your bicycle and ride over there. Of course, we're talking about 10 million years from now, so. And the North American plate is moving slightly this way, and the Pacific plate is moving this way, so you have a lateral movement this way, and every time that slips a little bit, then we have an earthquake. And you can see it goes right through. That's why I always hear about big earthquakes in San Francisco, because the fault goes right through San Francisco. And then at the northern end, this transform boundary turns into a subduction zone. I showed you that up there in Washington State when it hits the Juan de Fuca plate. Here's the fault, the transform boundary, and up here it turns into, it's transformed here, but it turns into a subduction zone up along here. This is a photograph of the San Andreas Fault, somewhere in California, probably. Here's a road. And if we could get a more aerial view of that, unfortunately, but if we get a more aerial view, you could see that the road, if you went to that road, you could probably see that it's been repaired again and again. It used to be a straight road. Now there's an earthquake. It gets offset a little bit. They have to go in there and make it connect again. You can see there's a curve here going like that. So it would be interesting to see that part there, to see what it would look like, to see that road being repaired each time there's a major earthquake. So, summary slide of all three of these. You have the divergent boundary. I know you've heard this before, but I'm going to summarize again. Divergent boundary, material coming up. It weakens this area. The material comes in here, it cools, mostly because of the ocean, and it forms a thin crust. The circulation pulls these plates this way. As it does so, it gets to the convergent boundary. It goes underneath here. This material is made up of rocky stuff, but also lots of fossils and carbonaceous material that has been gathered from plankton and such. So there's a lot of carbon dioxide in it. And it's also water soaked. Comes here, as it goes deeper, it melts, comes back up again, has volcanoes. Over here, when it comes to a oceanic plate, same thing. It's going to do the same thing. It's going to come up and form volcanoes. The volcanic material breaks the surface of the water and forms island arcs, forms volcanic islands. Over here we have a divergent boundary on land where the material is coming up, it breaks apart the less dense material, it breaks it apart, and eventually as it goes apart it forms a low land here. What happens to lowlands? Water comes in, and eventually it could spread apart and make an ocean there. And here are the transform faults going laterally across the divergent boundaries. All right. And then lastly we have a geologic hotspot. And this is where Hawaii comes in. The hot spot is in the middle of a plate. In the middle of the Pacific plate, there's hot material coming up. Now, apparently it's not hot enough to break the Pacific plate apart so that you have a rift there and then it goes in two different directions. But it's one single spot in the ocean. In other words, it's not all along. It's not all along the rift. It's only in this one localized area. And as the plate moves, there's a hot spot underneath this island. As the plate moves, there's volcanic material comes up and forms this island. And then it dies down a little bit. In the meantime, the plate has moved. Then the hot spot gets active again, and it forms this island, and so forth. So today, this is where the hot spot is. It's not that the hot spot is moving, it's that the plate is moving. So as the plate moves over this hot spot, material comes up and forms new islands, in this case, new Hawaiian islands. And here, the big island of Hawaii is the largest one, and there's material being added now. In fact, I understand that there's another island now being formed off the coast here from the hot spot going off. Over millions of years, the plate may move across the hot spot and the original volcano becomes extinct. These volcanically formed islands, there's no volcano there. If anybody's ever been to Oahu, there's a big, famous diamond head on the lower coast here. You've probably seen the photos of it. If you saw it, you'd know what it is. And it's this huge volcanic caldera, but it's extinct. You can go inside of it and look around and everything. And but you can see clearly it's a volcano, but it's extinct because Oahu's moved away from this hot spot. So there aren't very many, but Hawaii is in the middle of the Pacific plate, and we have a hot spot in the Yellowstone National Park. Anybody have ever been to Yellowstone National Park? That's where they have the geysers like Old Faithful and such. And you're going to see a movie on this at the planetarium. It's about supervolcanoes. And it has gone off before, and it could go off again. Hopefully not anytime soon, because it would be really bad. Anyway, geologic hotspot then is a place in the middle of a plate where material is coming up. So you can see here, Hawaii was formed about 3.8 to 5.6 million years ago, and so forth. So Hawaii, the big island, is about 0.7, about 700,000 years to present. You can see on this map, look at these islands here. These islands here, the Emperor's Seamount chain, this is one of the oldest ones up here, because this plate is moving this way. At one point, it was moving north. Now remember, this that was moving north was over the hot spot here. So the plate was moving north at some point and formed these islands. And then at some point, it changed direction and started moving more towards the northeast, probably with some stuff going on over here. And so all of these were formed, all these islands and such, this range here was formed by material coming up from this hot spot as the plate moved over and across the hot spot. And this is where it is today. And as this moves, we'll continually be adding more and more islands along there as we go. Islands if it breaks the surface. Again, Hawaii, this is the kind of volcano that you get. It's called a shield volcano. It's not real violent like Mount St. Helens or something. You've seen pictures of that where you just see these huge explosions. The volcanoes here are not like that. They're less violent. Obviously, you wouldn't want to be standing near it, but they're not these huge explosions. And they're pretty much going all the time. They're pretty much just going. They're just releasing material pretty much constantly. Here's some, I guess this in red here, these were formed by a hot spot at some point. And I talked about this here, how the plate must have been moving north at some point and then it shifted this way and started going that way because that's the direction that these are going. Okay, so in summary, and I've done a bit of this already, but this slide, and you have it in your notes, by the way. The oceanic crust is usually less than 200 million years. Continental crust, the thicknesses, compares the thicknesses and densities and composition, and it shows a summary of pretty much everything, the ocean to ocean. It's pulling down on here. You have a trench. You have material melting here, coming up and forming volcanoes. Material breaks the surface. You have an island arc there. You have rift valleys here where the material's coming up and pushing these plates apart. Transform boundaries along here. Here the oceanic crust is intersecting the continental crust and pulling it down. Along here you're going to have earthquakes as the pressure is released. It's the same idea as as these things slide apart. This is moving this way. Push your hands together, and when it releases the sudden pressure, you're going to get an earthquake and a vibration through the earth, and we feel it. And the material melts, comes back up again. So-called ring of fire. I showed you the slide earlier in the previous thing where the plates are all around here. They're interacting here. This is where the plates are intersecting. And so all along here, they call this the ring of fire because all along here we have earthquakes, volcanoes, and lots of stuff. So anybody living along here usually has to deal with major earthquakes or volcanoes at some point. Japan is a island arc made from ocean to ocean crust material coming up from that. Philippines, the Java, I don't know if you recall back in 2004, I believe it was, at Christmas time. I remember it distinctly because at that time I was visiting my family in Minnesota. It was on the news all the time. And there was that very large tsunami. And what had happened there was, again, that was an ocean to ocean, there's an ocean to ocean plates, and one was going underneath the other one, was pulling it down, and it popped back up. One of the plates shifted back up. Well, what's above it? Water. The water has to go somewhere. It pushes the water above it, has to go somewhere, so it's going to level back out again, and you've got a tsunami. And if they had the proper detection, they probably could detect that. They had some warning for it. The people on the coast didn't. I mean, you can't get the message out very fast, but roughly took about a half an hour or more for the water where it occurred to where it hit the land. So half hour to an hour. Here in Seattle area, something similar could happen. The Juan de Fuca plate could go underneath and the land could pop up. I saw a NOVA program on this. It was talking about this. But much less warning time. They said about 15 minutes, which 15 minutes is barely enough time to pick up the phone and start calling somebody and telling them that you got less than 15 minutes to do anything about. As far as the general public goes, not much time at all. In fact, almost none at all. So if that should ever happen up in this area, major flooding, major tsunami perhaps in the Seattle area. The end. And that concludes the plate tectonics lecture. I hope you enjoyed yourself. Please take good notes. And yes, the stuff pretty much that I talked about, unless I said otherwise, is testable material. There is a worksheet on this. Please do the worksheet. And of course, we'll have the quiz and the test on all this stuff. Again, this particular unit, it's not real long. There's a lot of stuff I have to explain to get to the point where there's not really a whole lot of material there. In other words, all you got to remember is divergent boundaries, convergent boundaries, and transform boundaries, and the hot spot, the characteristics of these, but if you know why it's happening, again, this class is about general physical principles. If you understand why it's happening, you can always figure out what the results at these boundaries are. Well, that concludes this unit, and I hope to catch you next time, and I had a great time doing this. Thank you very much.